One of the last things that we need to discuss within the atomic structure topic is the concept of fission and fusion. We're going to start with nuclear fission because this is the topic that is used or has been used the most in history. Nuclear fusion is something that is being investigated and technologies are being developed. However, fission has been applied and is relevant to the world around us right now. Nuclear fission occurs when a very large nuclei splits into two or more smaller nuclei, releasing energy as it does so. This doesn't regularly happen on its own or spontaneously. It usually requires the nucleus to absorb an extra neutron. The materials that, when they absorb a neutron and then undergo fission, are called fissile materials. You need to be able to at least recall, and if not complete, a diagram that represents the process of nuclear fission. So the target nucleus that we've got here represents our fissile nucleus. So this could be something like uranium-235. When it absorbs a neutron, a free neutron which could have been released by nuclear emission from something like beryllium-13, or it could just be a naturally occurring free neutron, it undergoes fission. It splits, releasing two daughter nuclei or two fission products and three extra neutrons. This diagram, this representation of it with either two or three neutrons, is something that you should be able to recall and potentially draw again in the future. The things that you need to be aware of about nuclear fission. The splitting of the nucleus into two smaller ones releases a lot of energy. Now this can be as kinetic energy of the particles, the two daughter nuclei and the neutrons, or it can be as gamma rays. Typically, if it's as kinetic energy, then that will make the material hotter, as these particles are going to be moving with some very high speeds, and the temperature of the material is dependent on the kinetic energy, or the average kinetic energy of the particles within it. There are two or three neutrons released. Two or three. It can be one, it can be the other. It depends on the fissile material involved, and even then there's a probability of it going to either two or three, depending on what the two smaller nuclei are. There's no hard fast rule here, but you do need to know that it is two or three neutrons released. But that leads us to a point that we need to make. Those neutrons could then theoretically cause further fissions if they're absorbed by other large nuclei or other fissile nuclei. In a nuclear power station, this is used. We use this idea to produce a chain reaction which releases a steady amount of energy, and I'm going to talk about that more in just a moment. But we use something called control rods, which are lowered into the nuclear reactor to absorb those excess neutrons, so that only one or so of the fissions causes another, and that allows for the steady release of energy. The energy that is released from fission can be used to heat water, particularly within the power station. And if you look back on any kind of revision materials you have linked to energy resources, you can see that the nuclear reactor just takes the place of the coal, oil or gas burner within the power station, heating water to turn it to steam, to turn turbines, to generate electricity from a generator. When it comes to looking at examples of chain reactions, I want to start by thinking about a nuclear power station and the controlled reactions that happen within there. The rate of the fission chain reaction within a power station is changed or controlled using objects called control rods, and these are literally rods of a material that can absorb any free neutrons that go through them, and by absorbing those free neutrons, that prevents them causing further fissions of their own. So the aim within a nuclear power station is to create a sustainable chain reaction which is giving a steady release of energy. So from this one fission that we have on the left hand side, each further fission causes one more. So control rods absorb two of those neutrons out of three and allow the third one to then go on and cause another fission with a bit of fissile material within the nuclear fuel, typically enriched uranium. And that process continues over and over again in order to give a steady release of thermal energy that can be used to convert water into steam, to turn turbines, to generate electricity. If the power station is required to produce more electricity, or then in order to do that, the control rods can be removed from the nuclear reactor or raised out of it, allowing more of those neutrons produced from fission to cause further fissions themselves. That will increase the rate of the chain reaction, therefore releasing more energy quickly. The flip side to a controlled chain reaction is an uncontrolled one. And in uncontrolled chain reactions, you're dealing with no control materials whatsoever. So the control rods just, quite frankly, don't exist. The first sustainable chain reaction was done in a squash court in Manhattan University, where scientists took thin discs of fissile material and placed them between a material that would absorb excess neutrons, and that produced at a steady rate a decent amount of thermal energy. This was all part of the Manhattan Project. The Manhattan Project went on to develop the first nuclear bombs, led by a scientist by the name of Oppenheimer. I've made this diagram a little bit simpler than it should be because I quite frankly ran out of space on the page. What you've got to do is imagine that every single fission is causing 3 other fissions. Just watch how quickly the page fills up. In virtually no time at all, you go from one fission to many fissions, each one releasing the same amount of energy, and with each step you get an exponential release of energy. So just to give you an idea of the numbers involved here, in a tiny fraction of a second you can go from having 1 to 3 to 9, 27, 81, 243, 729, 2187, 6561, 19,683. Now this is happening within a fraction of a second, and each of those fissions is releasing energy, thermal energy, gamma radiation, all at the same time. When you have an exponential release of energy like this in a very short period of time, you're dealing with an explosion. And that's effectively what this was used for. This is effectively what the research into this was able to produce. It weaponized fission for the first ever nuclear bombs. The scientist that developed this, I've mentioned his name already, was Oppenheimer. When he was doing this, and when he was observing this, he made an observation, and then in a later interview he was observed talking about this. So I just want to show you that clip.
We knew the world would not be the same. Few people laughed. Few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another.
Oppenheimer was basically making the observation that he realized from the sheer magnitude and the sheer volume of energy released from this reaction that this technology had the potential to destroy the world. One of the things that makes nuclear weapons, or one of the phrases that you regularly hear when you hear people talk about nuclear weapons, they talk about a nuclear deterrent and the idea of mutually assured destruction. If one country was to use its nuclear weapons in an act of war, other countries with nuclear weapons would be able to retaliate, and the net result would be a massive global damage, sufficient dust and rock thrown up into the atmosphere, radioactive dust and rock thrown up into the atmosphere, that it could cause a massive amount of global dimming and lead to a nuclear winter. And then on top of that, the materials that are released from these nuclear bombs when they explode tends to be radioactive, and that leads to the process of what's called nuclear fallout. So there are games that reference this idea of nuclear fallout and what a post-nuclear war world would look like. Most of it's based in fantasy, playing heavily on the ideas of nuclear radiation causing mutations, but the core idea that the technology of nuclear weapons could lead to the world becoming uninhabitable, at least for humans, is one that holds true to a lot of different themes within science fiction media and that kind of side of things. Time to talk about fusion. Fusion is in essence the opposite of fission. So whereas in fission you're dealing with a large nuclei splitting into two smaller ones, in fusion you're dealing with two lighter nuclei colliding, joining together and making a heavier nuclei. When that happens inside a star, it's typically in the first instance to do with hydrogen fusing into helium. When we talk about stars as part of the space topic, you'll understand a little bit more about the different stages that the star will go through. But on its most basic level, the start of a star's life, hydrogen fuses into helium, releasing large amounts of energy in the process. The larger nuclei has got less mass than the two smaller ones that it was made from. And now that sometimes causes issues, because people start worrying about conservation of mass, which is a real thing that you need to be aware of, that mass is always conserved within a chemical reaction. However, this is a nuclear reaction, and within nuclear reactions it is possible for some of the mass to be converted into energy. Those of you that want to look into it in a bit more detail can look up Einstein's relation, E = mc squared, and that basically gives an idea as to how mass and energy are the same thing. Fusion releases more energy per kilogram of fuel than fission. Now I mentioned already that fission is more efficient than burning a fossil fuel. Fusion, in theory and in the practice of stars, releases more energy per kilogram than the fissile materials do when they are allowed to undergo a chain reaction. But it requires a lot of energy. You need to get these particles moving, these nuclei particularly, moving very fast, incredibly high speeds, and have them at a sufficiently high pressure that they will collide and then combine. You've got to remember that the protons inside the nucleus all have a positive charge, and like charges repel. So in order for them to combine, in order for them to stick together, they must have sufficient energy and be moving sufficiently fast to overcome that repulsion force for long enough for the forces to exist between the two different nuclei, and then for them to effectively stick together. Whilst fusion reactions potentially do yield more energy per kilogram, this requirement of energy means that we haven't yet got to the stage of producing fusion power stations where more energy is produced than is put into starting the fusion reaction in the first place. There are things in place called a tokamak, which is a toroidal, basically a donut shaped fusion reactor where they can make fusion happen on the Earth, but to harness the energy released from that fusion, that is where the technology is still lacking at the moment. It's one of the areas where nuclear physicists are still researching in order to try and develop this, because once we can get fusion to work on the Earth, in terms of that, we have got a very potentially clean source of energy there. It requires hydrogen as a fuel, which you can get from the electrolysis of water, and then once that hydrogen is made to undergo fusion, it can release energy, and the products are lighter elements like helium, which are not harmful to the environment. Key things you need to remember about fission and fusion. Fission is the splitting of a large nuclei into two or smaller ones, which are more stable. It's caused by the large nuclei absorbing a neutron typically. When it breaks down, it releases more neutrons. Those neutrons can cause a chain reaction, and if it's uncontrolled, you have a nuclear explosion with an exponential release of energy. If it's controlled using things like control rods within a power station, it can provide a steady release of energy that can be harnessed to generate electricity. Nuclear fusion is when two small nuclei collide and combine to form a heavier nuclei. Some of the mass of those smaller nuclei is converted into energy. It requires incredibly high temperatures and pressures in order for it to ever occur. But because of this, fusion reactors are still being researched and developed. They are not yet a source of electricity or electrical power within the world.